So in this lecture we'll talk what happens when you have a 2D wave, okay, and you confine the 2D wave in boundaries. So y equals to 0 and y equals to b are two boundaries beyond which the 2D wave cannot go. So now imagine that you have a 2D wave and the 2D wave is traveling along this direction. Agreed? So so the best way to imagine this is, um, consider you have an infinitely long, you have two rods. These two rods are infinitely long, and what you do is you attach here two membrane, two elastic or rubber membrane to this infinite rod. Agreed? So your membrane is also infinitely long. So what happens when you generate a wave in the membrane? You can generate a wave in the membrane like this, or you can generate a wave in the membrane like this. So let me give you example when this type of wave is generated. So what you do is, so consider when you produce this type of wave in the membrane, okay. So this type of wave in the membrane is produced. See, as you can see that this is a 2D wave, okay. This is a 2D disturbance on a 2D membrane. So this disturbance is exactly moving in this direction, that is the x direction. But I'm not concerned with this. So consider I make some disturbance here such that the disturbance is going in this direction. So consider the same membrane, and this time you give a disturbance in this direction. Agreed? So when you give a disturbance in this direction, the entire vibration or the disturbance goes in the k direction. And since it is in any arbitrary direction, k can have two components, k1 and k2. Now can you tell me how can I write my 2D disturbances, that is z? So remember, so this is x and y, and the entire vibration is happening in the z direction as we discussed in our last lecture. So z, which is a function of x and y, okay, because z is a disturbance. So how can I write z? So let us see. So it will be a e to the power I, so omega t. Okay, now comes the main part. So we'll use the trick. What was the trick? The trick says if things are going in the positive, you put a negative sign. So you see the k1 is going in the positive x direction, so you write minus k1 x. You see k2 is going towards the positive y direction, so you write minus k2 y. So this is the trick. So this is my 2D wave that is propagating on this 2D object. So this x and y is the 2D boundary. X is the direction in which the wave is propagating and y is the boundary for the 2D wave. So here you can see, so this is the direction x in which the wave is propagating, and this is the y, and perpendicular to x and y is my z in which the vibration is happening. You see, these vibrations are happening in all z direction. But an interesting thing happens here. The interesting thing is that this k2, when it goes up, so there is a part of the wave, so listen to this, so there is a part of the wave, so this wave which is in k direction can be thought of as two waves, one propagating in k1 direction and one propagating in k2 direction, that is in the y direction. Agreed? Now the component of the wave in the y direction will become reverse. As you can see, it will become reverse. So as a result of which, this k wave, which has two component wave, one component wave has vector k2 and another component wave is vector k1. Now k2 vector will form a standing wave. Agreed. So what will be the other, forget that. So can you tell me what will be the other z? I mean the z when the k2 is opposite, when the k2 is coming downward. So when the k2 is coming downward, then it is actually taking a direction, it is moving in the direction of negative y-axis. So what will happen when there is a negative y-axis? So write omega t. Now look at k1. K1 is as it is in the positive x direction, so don't do anything to k1. But now since k2 in the other case is moving in the negative y direction, so this will be plus k2 y. Agreed. Now before going further, let us directly guess what is the solution. Let us guess. So can you tell me at the end of the day what will be my vibration looking like? Let me tell you how it will look. There will be some amplitude. Okay, remember standing wave? In standing wave what happens? In the 1D standing wave we saw that the space part and the time part, they get separate. Here also same thing happen, but with a catch. Now the problem is this K2, the K2 part of the wave will form a standing wave. Agreed? So K2 is responsible for a standing wave. So for a standing wave what should I have? I should have the space part left alone. So for the K2 part of the wave, so I will have sine K2 x. Oh, sine K2 y actually. So it will be y, because K2 is propagating, so K2 is oscillating between the two extreme y's, y equals to 0 and y equals to b. Now what happens to K1? K1 is very happy. K1, no standing wave is with the K1 component of the wave, that is the K1 form of the wave has no no standing part, and it is happily moving towards the x-axis. So for the K1 at the end of the day it will be sine omega t minus K1 x. So why K1 x? Because the K1 is moving towards the x direction. So this is the solution that you will get at the end of the day. So the solution, we just guessed the solution. It's very easy to guess. The K2 part will form the standing wave. That's why it is in sine K2y. Agreed. And the K2 part of the wave will satisfy what? You see, the K2 part of the wave, that is the sine K2, must satisfy. So what happens to vibrations at y equals to 0? There is no vibration at y equals to 0, and there is no vibration at y equals to b. So no vibration means there is zero vibration. So the K2 wave will have zero vibration at y equals to b, and will have zero vibration at y equals to 0. So what does this imply? This implies that my K2 will be n pi by b. Okay, why? Let us see why. Look at here. So let me write sine. So I tell that my K2 is n pi by b into what was here y. So this part is the wave of K2. So can you tell me what happens when y equals to 0? When y equals to 0, sine 0 will give 0. Yes, that is true. There is no vibration of K2 wave at y equals to 0. So can you tell me what will be this function when y equals to b? So when y equals to b, I will have sine n pi, because at y equals to b, the denominator b and the numerator b will cancel, and again I get 0. So amazingly, the K2 part, which is the sine n pi by b y, satisfies the boundary conditions. Now I just guessed the solution. As I said, I have just guessed the solution. Now question is how to actually get the solution. Now the actual way of getting the solution is, you see, write these two waves as we discussed. You just add them and you will reach here. This is another way. Agreed. And you have to make the guesswork. So what is the main guesswork that you need to do is, since your K2 will form the standing wave, so this is very logical to say that the K2 will be quantized, that is it will be n pi by b. Agreed. So this is the extra condition that you put on wave, which is 2D wave, which is traveling on a plane, and that plane is such that one side it is free to go, that is in the x-axis, and one side, that is on the y-axis, it is being bounded. Agreed. So we guess the solution, and you can also find the solution. Now, so we found that for this type of condition, the k1 the k2 will be quantized, that will be n pi by b, and n will take all the integer values. So let us work with only k. Let us work with only k. So since k is a vector, as we saw, and k is the direction in which the actual 2D wave is moving. So this wave can be imagined as made up of two waves. One wave has wave vector k2, and another component wave has wave vector k1. So can you tell me how k1 square k1 and k2 are related? Obviously, since these are vectors, they will be related like this. So k equals to k1 square plus k2 square. Agreed. So so I can write k square. So can you tell me what k will be? So k will be omega by velocity, because omega by k will give me velocity of the wave, so omega by velocity will give me k. So let me write it later on. So this will be k1 square, and what is my k2? K2 is n pi by me, so this will be n square pi square divided by b square. Agreed. So let me write uh, so k1 square will be k square minus this part as it is. Agreed. Now you know that for the wave to travel, both k1 and k2 are positive. Agreed. So k1 here must be real, only then the wave can travel. So for k1 to be real, this value of k must be greater than equals to this value. So k must be greater than equals to, so it should be not equals to, should be greater than, actually should be greater than n pi by b. So if k is greater than n pi by b, then I can write omega divided by velocity should be greater than n pi by b. So what is omega? So omega should be greater than n pi, v is the velocity of the wave, divided by b. This is called the cutoff frequency. Why it is called the cutoff frequency? Because if the frequency of the wave is not greater than this, so if the frequency of the wave is less than this, then the k1 will become unreal. And if k1 becomes if k1 becomes unreal, then this entire wave does not exist, then this entire wave would not exist. So for the propagation of 2D wave, the frequency or the omega of that 2D wave should be greater than a particular value, and that particular value is here n pi v by b, and this is called as the cutoff frequency. So what is cutoff frequency? So let me remind you, if you have two rod, and between the two rod if you place a rubber sheet, okay, so what you have done, between the two rod you have a rubber sheet, and you want wave to travel on the rubber sheet, then this wave will successfully travel to a large distance on the rubber sheet only when the frequency of the wave that you generated is greater than n pi velocity of the wave divided by b. What is b? B is the distance between the two rods between which you have kept your membrane. So this is what is meant by cutoff frequency. So if you have understood this, then you can easily understand the concept of waveguide in electromagnetic wave. The concept is exactly similar. 99% this derivation and the derivation that we will do in the next lecture is going to be same. So look at this lecture again and try to understand. Read some books so that you understand cutoff frequency better. Okay. So in the next lecture, we'll study waveguides for electromagnetic waves.